5 minutes past 2. I think we could start because we also have another meeting at 3:30, right?
Oh, right, yeah. Thanks for reminding. Okay, welcome back, everyone. So, because a lot of you had some problems um, with this experiment with the OT radio telescope data, I thought I'll go into some more detail as to how one would go about doing the analysis. So it will still be the concept level. I'll try to make sure you understand all the steps that are needed and why we are taking those steps. As far as the coding goes, there are ways you can simplify the process so that you don't have to depend too much on um, libraries and so on. As long as you just focus on trying to understand the concept behind what we are trying to do, and things should be fairly clear so that if you know just simple programming, you should be able to accomplish what you want to do with simple for loops and simple operations in Python or whichever language you're interested in. Okay, so at the very basic level, what we are trying to do is we are trying to measure the electric field that is incident on an antenna. We talked about this a little bit in the previous session as well, and you must have listened to it in multiple lectures by now. And essentially, you have to remember that the voltage, the data that you're getting out here is related to the electric fields that we are trying to measure. It has pretty much a one-to-one correspondence. You would also know that the voltages themselves are not directly directly the effect of just the electric field that is falling on an antenna. It has components due to the system electronics themselves. So the system also generates voltages, noise due to various components, and there is signal as well from an extraterrestrial source that we are trying to observe. So it's a combination of all, but in essence, uh, the, the, the voltage has components that correspond to the electric field that we are trying to measure. Now, in this OT data that we are using, we are observing in a narrow frequency range centered at 326.5 megahertz with a bandwidth of about 16.5 megahertz. And as Desh was mentioning about the reasons for down converting, there are many benefits to down converting these frequencies from these radio frequencies down to uh, the baseband so that what we are working with, the frequencies that are present in this voltage variations are limited to 0 to 60 megahertz. Okay. So in general, if you want to understand Fourier transforms, there's a simple visualization for it. Any function that is varying in time can, in principle, be reconstructed using sines and cosines. So in this example, we are taking a periodic function, and if it's a periodic function, then there is you can use the period of the function to determine the frequencies that would contribute towards reconstructing that function. And that is the Fourier series that you would have learned. And this is a visualization of it. In the top panel, you'll see that there is a, a repeating function. And in the bottom panel, you'll see a bunch of uh, sine waves of different frequencies. These are discrete components, and what you can change is the amplitude of it, the frequency of it, and if you combine it appropriately, it will reproduce this function in time. But because we have this set of frequencies, sine curves that are reproducing the function, you can also plot what frequencies contribute how much towards it. So essentially amplitude of the frequency that is contributing. And you see here in the blue axis, um, the amplitudes for various frequencies in the form of a comb tooth sort of function. So in between frequencies are not contributing, only these discrete frequencies are contributing towards it. And you can reproduce the time series perfectly. So what happens if the the time series we are interested is not periodic? Here is an example where we are taking a non-periodic function. It's essentially like a Dor function. And this function can also be reconstructed using frequencies, except you'll need to take a Fourier transform, and it will have a continuum of frequencies that contribute towards recreating this time series. So that is what is depicted over here. There's an attempt to make that make the two-dimensional space, uh, you know, uh, showing all the frequencies. But of course, it's a continuum of frequencies. You won't be able to show it very easily. But you can see the projection of it in the frequency space. And here, what you have is you have a freedom in amplitude of a particular a wave of a particular frequency, and also the phase with which you're combining it. And once you combine a continuum of these monochromatic waves at different frequencies obviously, but also different amplitudes and different phase, that are two numbers associated at each frequency, then you can reproduce this particular non-periodic function. The only difference for in our case, okay, before that, so in a Fourier series, we saw that you have a honeycomb-like structure where you have discrete contribution from, discretely spaced frequencies. Here you have a continuum distribution. This is for non-periodic functions. The only difference between the example that is shown and our signal is that ours is not so well localized in time. The stored function is essentially zero, other than the place where it's a single constant value. Ours is something that is still, it's generally a general signal with all its noise components. It's not going to be periodic in any way. And that can also be reconstructed in the frequency space using a continuum of frequency components. And that's what that is what you would consider as taking the Fourier transform and finding out the Fourier components of a particular time series. So the question is, why do we even want to do that? You have a time series at hand, which essentially comes from the electric field that we are measuring. Why we are interested in this frequency information. For this, you'll have to take a look at the phenomena in a different way. So at the point of measurement, which is at the telescope field, let's say, we are measuring the electric field, which itself changes in time, which is the time series of the electric field. And you can view this as a superposition of waves of different frequencies. This is radiation. We are talking about radiation here. Let's say there are monochromatic waves, that is waves of individual frequencies uh, uh, that are superimposing and then creating the electric field the net electric field that is produced at a point and we are trying to measure. And essentially, if you take a Fourier transform of this change of this electric field with time, you will you will get the individual frequencies that go into constructing this that went into determining the time behavior of this electric field. Is this part clear to everyone? In case you have any questions in between, you can interrupt me and ask me. Also, Desh, if you want to add something at any point, you can always unmute yourself and add in.
Yeah, there is a question, Prakash, on YouTube. Yeah. So what is the need of town conversion?
Oh, I think one of the reasons is it's just easier when you discretize it. So you have these analog signals that you're converting and storing in your system. And I think at lower frequencies, it's easier to deal with it. There might be other reasons. Maybe Desh can explain it better.
Yeah, to do some operations.
Yeah, there are three distinct reasons. there could be more, but three well appreciated reasons. One is that putting a mixer with a tunable local oscillator, doing this conversion in frequency without changing any information, does bring in a facility of tunability. If you want to select a particular band out of a wide band that is available at the input, instead of changing the entire electronics to tune to that new band, you can convert it into a fixed band at the output, where the local oscillator beating does the needful shift to a standard frequency at the output. So this brings in the tunability of the selection of the input spectral section. Second is, if the conversion is at a lower frequency, which always need not be, the electronics is cheaper and more easily configurable at lower frequencies. The losses in the system are less if they have to be transported across some long cables and things like that. So it's always easier in terms of ease of building a high gain chain that you would necessarily require to amplify these weak signals. Number three, any leakage that might occur. In the process of amplifying these signals by almost factor of 10 to the 10 or 100 dB in other words, even any small leakage can go back to the antenna if we have amplified at the same frequency as the original one. And then that can, based on the phase relationship of the leaked information, it will beat with the or interfere with the incoming signal, and you might produce either oscillation or saturation depending on the phase. This is to be avoided, particularly because these leaked signals can be way stronger than what is coming from the sky. So this is avoided by changing the shirt of the person. Only, let's say, yellow shirt people are allowed in the input, which is basically saying that this is the spectral range the antenna responds to and the rest of the immediate electronics responds to. And then after the person comes in, you change the shirt so that even if he steps out, the person is not allowed in again. So these are the three basic reasons.
Yeah, thanks, Tesh.
So doesn't the leakage occur during that part while we are converting frequencies?
Can you say it again?
So doesn't the leakage occur at that time when we are converting these frequencies from one to the other?
No, it's a rigid translation. If you, we know that, for example, if you take a time sequence and we shift it rigidly, there is no change of information. Much the same way in the Fourier domain also, it's a rigid shift. A band centered at certain frequency is literally shifted, okay, rigidly without changing the internal relation of the tones in the band of interest.
Okay, so the band of which the frequencies we are will be same band in the other part also.
Yes. So in fact, no change of information. By any shifts, scalings of the axis, okay, common scaling of the axis, which is like saying if something is Doppler shifted, the information does not change. It's just represented in a different way. So as much as we know that simple shift of a function in time does not change the information content, the details of the variation across time. Similarly, the same thing holds good in its Fourier counterpart as well. A rigid shift there does not change the information.
Okay, yes.
And this is assuming, of course, and reminding ourselves that all these operations are to be done in a linear fashion. Okay, they're linear transforms or translations. So they do not mix one frequency information with another frequency information within the band.
Okay.
Okay. So at this point, I hope it's clear to everyone that we are trying to measure the electric field from the radiation that is falling in. And the electric field vector is a superposition of contribution from individual waves of, you can view it as a combination of contribution from waves of different frequency or in a frequency range that are superimposing and creating this net electric field that we are trying to observe. So it has this frequency content in it, which is apparent in the way it changes with time. Okay, and since the power of this radiation field is proportional to the square of the transverse electric field, we can get a power spectral density of the incident radiation itself if we measure the electric field values. Okay, but so we are interested in the electric field, we are getting voltages which essentially carry that signature. And if we do the same bit of analysis here, we try to see the frequency components and contributions in these voltages, determine its power spectrum, we'll be able to get an idea of the same for the electric field that we are trying to measure. Okay, in this activity, so essentially once you realize that that's what these voltage signals are, what we are trying to do is, first of all, just visualize the time series, analyze the statistical properties. This most of you have pretty much done. The next thing is determine the spectral composition. As you saw, like it's a time series, we are trying to figure out what frequencies contribute how much towards it. Get the power spectral density through the FFT. Then we are trying to, we'll try to visualize the power spectrum, which is essentially this power spectral density, how it changes with time. And then once we see a signal, we'll try to, I mean, we know it's a pulsar signal, and we'll see that it's dispersed in, it has dispersed in the frequency range. And we'll try to de-disperse it, fold the pulses, and get the approximate period and DMs, the dispersion measure. So we'll go through that somewhat step by step. So if you try to plot the voltage time series, or at least a section of it, this is about 1/3 of a second plotted, it is just going to look like this. Fluctuations about approximately 0. It's both north and south. You'll have to zoom in quite a bit. Let's say you take 100 samples, and then you will be able to see it in more detail, but still it will still be these random fluctuations out of which you won't be able to see if there is any signal or not. As we know, these voltages, when you these voltages will follow a Gaussian distribution. This you can verify by plotting a histogram of the voltages. And for the north and south, you can do it separately. You can then combine the voltages and do it together. And you can calculate the mean and standard deviation. We discussed about how a constant DC component can actually shift your voltage mean. And that can, of course, be subtracted out or then later clipped from the power spectral density distribution. The squaring of the voltages can again be visualized as a time series, as you can see over here. So you have only positive values because of squaring. And if you plot the distribution of it, you'll get a function that has exponential decay. So this is the functional form on the left. I supplied a link as well in the notebook as to how you derive this from the Gaussian distribution that you had earlier. So you can take a look. Now coming to the part of finding out what spectral what frequencies are contributing towards this spectral, this time series variation. So in the top panel, if you'll see, I have taken about 512 consecutive voltage samples. So this is a time series, a small chunk of the time series that we have. And as described earlier, Fourier transform, in this case, a discrete Fourier transform, will give you the n/2 frequencies that contribute towards this time variation. And it will give you the amplitude. Initially, when you take the FFT, it will give you the complex amplitude of what frequencies contribute how much. Now, this complex amplitude essentially is the magnitude of it and also the phase, which is at what phase they are combined to get this time series. If you take the absolute value square, you'll get the spectral power, which is plotted in the bottom diagram. So this is for just one set of 512 samples. All you have to do is, take the first 512 points, run the FFT, take the absolute value square, and you can plot 256 channels, frequency channels of this power distribution. Now, what essentially we have done by doing this is that we had initially a time series with a resolution of 30 nanoseconds, which here we are using the variable dt. We are taking n point Fourier transform, in this case 512 points, and hence and with that we are getting a single spectrum for that time bin, which is n star dt. In this case, I think it will be about 15 microseconds or so. For which, so in that 15 microsecond bin, you have one spectrum instead of 512 voltage samples. Now you can do that in a loop. You take the first 500, that is the top left corner voltage time series. After that, it is the next 512 and so on. This is the third set and so on. So you can break up your voltage time series into chunks of these 512 samples each, and you take the Fourier transform to get the spectral amplitudes, and then you take the absolute value square, you'll get the power spectrum. So this should be clear. And at this point, I should mention, if we are having problem with libraries like NumPy, hold on, somebody has a question.
What is the frequency bin here? Will you please?
I have, yeah, okay. Here I have just given these frequency bin numbers, but you can actually calculate it either using the command RFFT frequency. It will give you what frequencies it's giving in, or you can go back to the formula and you can compute it yourselves. So if it will be essentially 16.5 megahertz is the total bandwidth, correct? And we are dividing it into 256 channels, ignoring zero. Yeah, it will, I mean, this particular FFT will give you 257 bins, but you ignore zero, you'll get 256. So you divide 16.5 by 256 and it'll give you the frequency range which we are probing. Is that clear?
Yeah.
Yeah, that's the frequency step. You can also alternatively calculate it by using the entire length of the data in time, and inverse of that will provide you a number which will define the separation between successive frequencies.
Right. Okay. Now, what you have at this point is for each of this time bin, the size of which is about 15 microseconds, or the number of FFT points you use times the time resolution. In each of this bin, you have a power spectrum. So you'll have a series of these power spectra, right? Yeah, I was about to say that I see that a lot of people were struggling with NumPy operations, for instance, trying to use its methods. If you're unfamiliar with those libraries, I would suggest just use a simple for loop. it's, I mean, it should be fairly straightforward to successively take 500 points of a voltage time series, and then in a loop, find its Fourier transform, absolute mod square, get the power spectrum, store it in a different array, and get the final array. So that is the simplest, so that you don't have to worry about which axis you need to take Fourier transform over, and or inadvertently make any mistakes doing that. So in the top panel, for instance, I've shown you 5 consecutive power spectra that were obtained. But of course, this will keep on extending as you take, you'll see that they're all different according to the time chunk you have taken, but it will all be taken from consecutive sets of 512 voltage points. Once you have that, for improving the signal to noise ratio of this spectrum, it's advisable that you combine these consecutive power spectrum, let's say 30 or 50. In this case, I've even done 100 of these power spectra, and get an average of some or co-added spectrum, which will have much better time statistical properties. For instance, you can see in the bottom, it is essentially the average or sum of about 100 of these power spectra, and you can see that the signal and the noise, the noise level, which is essentially the fluctuations in between, is much smaller compared to the contribution at individual frequencies. Now, once you do this, the advised values, let's say 30 or 50 of these power spectra that gets added or averaged into a combined power spectrum here. So there is, so I've suggested in the notebook that try to add so many numbers that eventually your bin size is still less than 1 millisecond. This is important considering we are looking at Pela data, which has about 68 millisecond period. But if you slightly go under or over, it may not be a big deal. So what you have essentially now is a series of these sort of improved power spectra for the entire voltage time series that you have now converted into these series of power spectra. Now, that is what a dynamic spectrum is essentially. A dynamic spectrum is this sequence of power spectra plotted as a two-dimensional plot. Or, I mean, if you can, plot these things as in sequence, and you can visualize it too as a waterfall plot, but you can also do it in these 2 dimensions. One now is time, that is each frequency bin over here, it will be very tiny over here, is this one spectrum going from 0 to 16 bandwidth originally, but here only the axis has been changed so that it reflects the observational frequency, which is centered at 326.5 megahertz. So although the voltage signals themselves are varying between 0 to 16 megahertz, we have just shown it in terms of the observed frequency so that it's, I mean, it's more closer to what we are trying to observe and characterize, so it helps. So this is how, once you get the power spectrum, the dynamic spectrum, this is how it should look like. In a few cases, you'll see that it will be flipped. So what are the main things that you see in this dynamic spectrum is that clearly these repeating streaks that are all inclined, right? And some vertical lines and some horizontal lines that are very narrow, or in this case, somewhat broad. But these are essentially the things that stand out from, let's say, the general patch of the dynamic spectrum, which looks just like noise. Now, these vertical and horizontal narrow lines are all likely radio frequency interference, either from something in the system or from outside that the antenna is picking up. The slanted streaks over here are the repeated signal from the pulsar that we are interested in. Now, in a few cases, you'll see that it's a bit flipped so that no, okay. At this point, it would be very important for you to know which axis is time and frequency. Obviously, that may be easier because the dimensions are very different. but it's also important to know for sure in your plotting which way the direction and the frequency increases. Depending on whether you're using IM show, which essentially plots the first row at the top, the second row below it, and the third row after that, and so on. Or the P color mesh, which starts from the bottom, plots the first row, and then stacks the subsequent rows on top of it. It would look very different. So you'll have your dynamic spectrum as a matrix, or an array of rows, which with each individual row having the spectrum. So it might be clear to you which way the spectrum goes. In a particular row, it will start with lower frequencies to higher frequencies. And as you go down these rows, it is increasing in time. Now, when you plot it, make sure you're able to make this one-to-one correspondence so that you know the flow of time and the spread of frequency. And in some cases, when I say this pattern is reversed, what you'll see is that these signals will first appear at lower frequencies and seem to go to higher frequencies as you increase in time. So it will essentially go from, if you plot time on the bottom axis, increasing towards the right, and frequency increasing towards the top on the left, or the y-axis, you'll see that there are streaks that start from the bottom, lower frequencies, and it'll go to higher frequencies as the time increases. This means that the frequencies are actually flipped. This is a problem with the data itself. So as long as you manually flip the axis of the frequency, you're good. So that each row which corresponds to the power spectrum, you just do a flip of it so that the last point is now the first point and the first point is the last point, and in between everything is flipped as well. And then if you plot this, you'll get the expected dispersion of the signal. Now, a few of you were unclear about what this dispersion itself is. I'll show you the formula in a bit, but essentially the interstellar medium, it's presumed that the signal at all frequencies is originating at the source at the same time. They are emitted simultaneously. And what happens is, due to interstellar medium, essentially the free electrons, the lower frequencies are delayed with respect to the higher frequencies, which is what is shown visible here clearly. That, for instance, you take one of these bright streaks, you'll see at higher frequencies, you see the signal first, and all subsequent frequencies, you can see systematic delays all the way up to the lower frequencies, where it's significantly delayed compared to the highest frequency signal. And this delay is something you can measure in the time axis. Okay, till this point, things are clear to everyone? Does everyone have any question about the dynamic spectrum, or how to get the dynamic spectrum?
Yes, sir. So the frequency bins.
Yeah.
Yeah. So the issue was that I am not sure. So we have to first consider, like, we are considering 512 points at first.
Yes.
Right now I'm talking about the GMRT experiment, but I think it's similar because,
okay.
Right. So we are considering 512 points at the start. And right now I figured out a way. So there was this command in Python called FFT frequency.
Yeah.
So from that, I like, you input the values, how many bins you have to divide it, and what is the number of values you need.
Okay.
And then you multiply it to the frequency band you need over, right?
You're saying, if you're talking about the command FFT FFT FREQ,
yes,
it should give you the frequencies automatically, because it will take in a parameter called the time resolution, right?
Right.
So if you provide the time resolution properly in seconds, it should give you the frequencies directly. But again, okay, this frequency will be between 0 to 16. It will give you the bins between 0 to 16. Sorry, 0 to 16.5 megahertz. Is that part clear?
So I'm not really getting this. The thing is that, okay, in the FFT frequency, we provide the, okay, how many values we need for FFT frequency, and we provide the time resolution. So it will give us the bins directly.
Yes, it should.
Yeah, in fact, I think it tries to do the optimum thing where there is no change of amount of information. So if you give n points in time, right, n pieces of independent information in the extreme case, you will find that it will translate it to n independent pieces of information even in the Fourier domain. Now, if they come as complex numbers, while the original data were given as real numbers, real numbers, you will find that you will get n by 2 complex numbers representing the same information in the spectral domain. And then that implies a certain stepping in frequency, which is implicit, and it's related to the inverse of the time span that you have taken.
All right, sir. Okay, thank you.
So you have no choice in this particular case, particularly use of these routines, in deciding the spectral resolution. Once you say these are the number of time samples I would like to Fourier transform as a set.
All right, sir.
You can, of course, do your own calculation to compute contributions in between the pieces, locations of frequencies that the routine like this would have chosen. But you can be assured that if you do compute contribution in between, you will find that it's not independent pieces of information. It can always be constructed out of the available values as through interpolation.
Okay, so all those listening, is it clear how to get the dynamic spectrum?
Sir, in dynamic spectrum, the x-axis we define is time, whereas y is frequency, and the color patch which we can see is the power spectrum, right?
Yes. Power
So,
spectrum.
do we need to define all these three variables in matrix form? Because I am sure and the color mesh takes only one input as a variable.
So you will have a two-dimensional matrix where each row is a power spectrum.
Okay.
Does that make sense?
Yeah, got it.
Or it is intensity as a function of time and frequency, and the intensity is described by the color.
So, sir, then there will be two matrices, right? One, one of intensity in the function of time, and one in the function of frequency.
They will
No.
each one of them will not be a matrix. It will be a one-dimensional array. Okay, but when you describe the intensity as a function of both, then you will get a matrix,
Okay.
which is what we have. At any given time, when you compute a spectrum, the way Prakash has described, and integrate the power spectra over, let's say, a millisecond or something, you get one column of this diagram.
Okay.
Such columns computed from different time sections, consecutive time sections, stacked together from left to right, will give rise to this diagram.
Okay. Thank you, sir.
Yeah, as I was explaining, if you choose to do it in a for loop, you take these 512 samples, get a power spectrum out of it. That is one array of power spectrum values. Now you will do it multiple times and you'll have with you a set of uh, these rows, which now becomes a matrix. Now these rows are always, every single row has the frequency bins, and across the rows, if it goes from one row to the other, it represents advancement in time.
Okay. Okay. So whenever
You
we can,
Prakash, right? In this particular,
Say that again.
you move across columns, right? And then you move across time in this particular diagram.
Right. In the diagram, it comes out like this. It's just that when you do the task, you will generate a row by default, and you'll keep on adding.
okay.
Yeah, I meant it. Yeah. If you run it in a loop, you'll create this row, and then you'll keep on adding these rows to produce a matrix.
No,
So
I
that's
mean
what I
column,
meant.
just
But
to
yes.
avoid confusion.
Yeah. I mean, if we take this image as a reference, then of course, this single column represents the power spectrum,
Yeah.
the
Okay.
frequency
That's all.
bins,
Thank
and
you.
then you go ahead. Yeah.
Okay. So
But make
sir,
sure whatever type of matrix you create, you understand what the rows represent and what the column represents
sir,
before plotting. Go on.
sir, actually, like here, after taking Fourier transform, the domain will be changed to frequency, and then we will calculate the power spectrum. So whenever we calculate, like plot power spectrum versus time, then it will like the the function which will have will be like in represent like what you can say, uh, will represent in both the domains, right? I mean, the both the variables will be included in that instant only, right?
Uh, Let me
Yes.
go back. Maybe I don't quite understand. So you have a power spectrum like the plot that is shown in the top left over here, right? This is in one time bin. So if you see the bottom, you have all these time bins for a total of 1 second. And the leftmost sort of column, which is barely visible over here, probably not very easily distinguishable, is this one power spectrum that has been plotted from lower frequency to higher frequency, lower to higher.
Okay.
Does that make sense?
Yeah. Got it.
Were you asking something else or?
No, sir. Yeah, this the same thing.
Okay.
Yeah. Thank you, sir.
Yeah, so you essentially have to imagine these particular values being plotted as a color plot over here. Then you take these values, plot it right next to it, and so on.
Okay. Thank you, sir.
Okay, I think is it fair to assume that everybody listening understood till here? Okay, I hope that's true. So what we have here is the dispersed signal from the pulsar, and and it is periodic. So these are the two things that we see from the signal. Now at this point, you can, I mean, I put the spectrum averaging after the dynamic spectrum just because sometimes it is flipped, and the flip is more obvious in the dynamic spectrum than this average spectrum. In principle, you can do this average spectrum. This is essentially these power spectra that we got in series all averaged together for the entire data. And then you can do the dynamic spectrum, see if it's flipped or not, and then go back, flip it, and plot it the right way. But here, I've made sure using the dynamic spectrum that it is in the patterns are all right, and then created the average spectrum. So this is again, as I said, is combining all the power spectra together. Okay, now dispersion itself, as I explained, delays the lower frequency signals compared to the higher frequency, follows this particular form, where compared to infinite frequency, the delay of the signal at a particular frequency nu expressed in megahertz according to this modified formula. If you express the frequency is megahertz, that is the observational frequency, not the scaled down frequency, but the observational frequency, because that is what is getting delayed in the interstellar medium. You use that in megahertz and you use a dispersion measure for the pulsar, you'll get the delay compared to infinite frequency. Now, what we have is a frequency range. So the the equation can still be applied. And as to begin with, let's assume we don't know the DM, we cannot look it up somewhere. In principle, the data itself can be used to come up with a rough idea of the dispersion measure. The way you would do it is essentially pick two frequencies wide enough, and then try to see when the signal arrives for a particular streak, for a particular signal. You'll see at what time. For instance, here, 330 megahertz. It has, the relative time is good enough. We don't need any absolute time. It comes at about 405 milliseconds after the start of the observation. And similarly, you can find it for a different frequency. What is the time at which it comes, as long as it's from the same, part of the same signal. This presuming that this was emitted simultaneously at the source. Now, the expression that you saw earlier can be written for two different frequencies and to get two different delays. And that can be inverted to calculate an approximate DM. So that if you have the frequency values between 2 points and the delay between these 2 points, you can get a rough idea of the dispersion measure. Okay, this part should be straightforward. Similarly, for periodic, for obtaining a rough period, what you can do is again look at the signal in the dynamic spectrum, see at in a particular frequency bin, what is the time between two consecutive streaks, two consecutive pulses in this case. And that would be the rough period for now. So how do we do the de-dispersion? We essentially have to compensate for the delays according to the delays that we calculate for different frequencies. And then by compensating, you would see that this time series, the individual time series at different frequencies will have to be advanced in time. So that is what these lines signify. What you can do is you can pick a high enough frequency as, okay. Yeah, so you have this expression, which is for a particular frequency, the delay with respect to infinite frequency. But what you can do is you can take two different frequencies, write the same expression. And since you have a rough value of the DM from the task that we did earlier, you can substitute that here, find the expected delay between any pair of frequencies, right? So either you can pick a high enough frequency in the band itself, and then calculate for a given DM, for a approximate calculated DM, what is the expected delay at lower frequencies. And then you have to, if the delay, for instance, it will come in, tens or close to 100, maybe even 100 milliseconds, then you'll have to advance that particular frequency time series. It is essentially a time series over here in frequency. So you'll have to advance it so that this thing gets aligned with the signal coming at higher frequency. So once you do, this is called de-dispersion, where you're compensating for all the delays at lower frequencies with respect to the higher frequency. So once you do that, you'll see de-dispersed spectral series that looks like this. Desh, is it still accurate to call it a dynamic spectrum, or?
Yes, it is a dispersed dynamic spectrum.
Okay, sure. I was just wondering, yeah, it is compensated with respect to a particular source, so the rest of the signals are probably sort of out of sync. So, but yeah, you can call it a de-dispersed dynamic spectrum. So
yeah, it can be the center frequency as well. So, it retains the arrival time. The de-dispersion, the delay adjustments can be done with respect to the arrival times associated with the center of the band, so that the reference is still kept to the center of the band in terms of arrival time of the pulses.
Right, right. And that is, if you see this, that is exactly what has been done here. I chose a central frequency, in which case the higher frequencies will need to be delayed. So either you take the higher frequency and then higher frequency, let's say somewhere like above 330, and then compensate for all the delays at lower frequency, or you can see how you can take a central frequency, let's say a point over here, and then the higher frequencies will need to be delayed, whereas the lower frequencies need to be advanced, so that they are compensated for this dispersion. Since we are not working in some absolute time units, this is fine. We are not really concerned about at an absolute scale of when the pulse arrives. We are just interested in the relative time scales of when the pulse arrives at different frequencies. So you'll see that this is exactly what has been done with respect to the central frequencies. The rest of the signals are aligned. Yeah, I believe there was a question from someone.
Yeah, sir, could you explain once again how to find the dispersion measure? I kind of lost you there.
Okay, so you understand what dispersion measure is, or dispersion is?
Yeah,
Can you explain it?
yeah, when the lower frequencies are delayed in time when arriving as compared to the
Yeah,
higher
so
ones.
so the idea is they are emitted. So a pulse is emitted at all frequencies at pretty much the same time simultaneously at the source, which is, if you look
Okay.
very close to the source, it should look like this bottom panel. The pulses
Yeah.
are emitted at the same time. But what happens is, as it traverses the interstellar medium, the lower frequencies are delayed compared to the higher frequencies, which means that if you look at the time series, you'll see that the higher frequency signal is seen first in time, around, let's say, 400 milliseconds, you see this higher frequency component. And then at lower frequencies, you'll have to wait another about 100 milliseconds before you see the same signal at lower frequencies. So you can see if you had two antennas, one at higher and one at lower, you would observe them at a delay. The lower frequency antenna would observe the pulse at a delay with respect to the higher frequency antenna. And the delay is quantified by this expression, this dispersion delay expression, where the expression is given in terms of infinite frequency. That is, you can imagine, okay. So you can imagine, with respect to infinite frequency, at a frequency nu1, you'll have a delay t1. Is that correct? Similarly, you'll have, corresponding to nu2, a delayed t2. And all we are doing is subtracting one from the other. So you have two expressions. And that is something we can, these values of nu1, nu2, t1, t2 can be obtained from the dynamic spectrum, or this matrix that you have. It's more obvious. I mean, you'll get an approximate value with the dynamic spectrum, but that would be good enough for the initial step. So the delta t over here is I mean, I could have written it as t1 minus t2.
Okay, so we take the difference between the highest and the lowest frequency in that thing, and the
It is useful.
difference. Okay.
Yeah, it is useful to pick a frequency both in high and low end where the signal is visible, because if you select somewhere here, it's not clear where exactly the pulse is, or even here.
So as long we'll see where it's visible, like at the extremes, and then take it.
Yes.
Okay.
Yeah, assuming that the bandwidth is small, where the nonlinear trend can be approximated to a linear delay trend as a function of decreasing frequency, you can even imagine this to be a line fitting process, where you can fit a line and you are trying to estimate the slope, which is inversely proportional to the dispersion measure.
Okay. Thank you.
Yeah, this would be a good exercise for later. I mean, after the winter school, if you ever get a time, want to work with this data some more, you can essentially, as Desh was mentioning, can get a series of these frequency and time values and you can determine the DM more accurately. So you get the approximate DM. The DM remains the same across the frequencies. So then you use that approximate DM to calculate by what amount these individual time series, that is time series at different frequency bins, need to be advanced so that you get this de-dispersed signal. So what you can do is you can combine all this contribution in time, in frequency. The plot at the bottom is essentially where contribution from all different frequencies have been added. So the two-dimensional matrix on the top has been collapsed along the y-axis so that you can see the pulses. So these are the pulses from the Vela pulsar. They should, correct me if I'm wrong, these variations in the pulse height are due to just intrinsic variability for Vela?
Yeah, they can be intrinsic as well as some extrinsic variations, except that for this pulsar, the scattering is significant. So the frequency scale on which and the time scale on which you will see scintillations are not on the scale of the pulse period here. So yes, all the variations that we see here, we believe are intrinsic.
Oh.
From pulse to pulse.
Okay. So the approximate DM value that I got was about 67.7 parsec per centimeter cube, and that was used to correct. I mean, if it's a bit off here and there, it shouldn't matter. So you can, once you do it according to the values you get, you can see the effect in the de-dispersed dynamic spectrum. You can imagine now if we hadn't actually de-dispersed it, how this particular integration over frequency would have looked. So this is, for instance, the plot of combining all the frequencies without de-dispersing. The signal is entirely smeared out because of these long dispersion curves in frequency. So once we have that, now even with this plot, you can find, you can come up with the approximate period. That is the difference between the peaks, let's say. And what you have to do is fold it. Folding, essentially what it means is you use that period, you know the period between these pulses. So you take the first, in this particular frequency integrated time series, what you do is using the period as a modulo, you keep on adding or stacking these pulses on top of each other so that you get a single pulse, single integrated pulse. So that is essentially what's done over here in the bottom panel. It has been folded and then it has just been repeated so that it's clear. Usually this is something we do to show the pulses more clearly. That is, the pulse itself, the data is just repeated again once, so that if you any periodic behavior or interpulse or things like that could be seen easily. That is what is done. So the stacking of all these pulses essentially gives the data between 0 to 1. What you'll notice is, as Desh was mentioning, there's significant scatter broadening of this profile. Essentially what it does is, it spreads out the contribution due to the pulse. Uh, this is due to this multipath propagation of these radio signals, where it will go through a lot of scattering media. And then the signal that originated around almost simultaneously will arrive slightly later and later, compared to the path of the shortest travel path. It will usually come later, and hence there is this spread after the pulse. This is very different than the dispersion we were talking about. This is just due to effect of scattering from the material in between. So finally, this is what you'll get from going from voltage data, starting out with voltage data to getting the pulse profile of the Vela pulsar. I thought due to time restrictions, this is.
I think there is a question about folding, Prakash,
Okay.
in the chat.
Yeah, let me take a look. How folding is done? Okay, you can. Okay, this I wanted to say even for other processes. I mean, this is similar to what Desh was explaining before. Like if you want to understand, like conceptually, you might understand right now what we have to do. That is, we have to stack, let's say the peak over, the second peak over here has to match with the first peak. So you can imagine this point added to this point, and so on, so that you get a single profile that is a combination of all these pulses. But if you really want to know how to code it, you can think of a simpler problem. Let's say you start with an array between 1 to 10. So it's an array of integers. It has 10, essentially 10 elements from 1 to 10. And you can repeat this particular array 10 times. And you can convert that into such a linear series so that you have a one-dimensional data going from 1 to 10 and then again from 1 to 10 and so on. Now we have to write a code so that 1 is added to the first one, all the ones are added, all the 2s are added, all the 3s are added, and so on. So that eventually you'll get a single one-dimensional array, which has 10 as the first column because it added all the ones. It has 20 in the second as the second element because it added all the 2s, and so on. And that is what we are doing here, except our modulo, that is the length of the array that we are choosing to sum over, is determined by the period. So if we have a period of, I think it used how much? Yeah, 89 millisecond period, then you have to determine how many points that does that correspond to in this time series, in this frequency integrated time series. It will correspond to a particular number of bins. And you just have to take one set of those elements and then take the next set of those elements and add them sequentially. Does that make sense? So let's say there are 100 points that span 89 milliseconds. Then you'll have 100 points of this time series. Take the next 100 points and add the first element with the first element of the previous array, and the second element with the second, third from third, and the last from the last. And you do that for all these, how many? 11 pulses.
Yeah.
Is that clear, folding? Is there a...
May I add some operational convenience? Okay.
Yeah.
So you can simply take the index of the sample number that you have in this series. You in the same units of the sample number, you can have the period handy in terms of units of number of samples. And now you take any sample number I, you divide that by the period in units of this sample number, and take only the fractional part of the of this division, and that you multiply by some other n over which you want to represent this profile. You will find that it will give you the index of the time bin of the average profile where you should add. Of course, you will get this number also, which is not an integer in general. And so you can take the rounded off value of it to begin with. There are other sophisticated ways of interpolation and so on, which you need not get into right now unless you wish to. So the simple formalism of the index of the sample divided by the period represented in units of the sampling interval that you have, which is period divided by delta t, which will give you the number of bins or samples across a period. So if you take any ith sample, divide that by this number, throw away the integer part because you're not interested in counting the pulse number, you're interested in the relative location of the sample in the folded version. And that you multiply by some other number if you wish to, okay, 100 or 50 or whatever it is the number of bins over which you would like to represent the average profile. And that will come out as a real number. You can take the rounded off value of it and decide the index of the bin in which you should add this sample contribution. You do that, repeat this process for all i's going from 1 to the end of the series, and also keep track of number of samples you have added to each one of these output bins, and do the division to get an average contribution. You will do reasonably well.
Okay, anyone has doubts? Yeah, Mohammed.
Excuse me, sir. Yeah, so like the entire x-axis
Can you
we have
speak up,
represented.
Mohammed?
Is it audible now?
Yeah, yes.
Yeah, am I audible now?
Yes.
Yeah, so the entire x-axis has it contains all the points. I mean, like the 30 something, like all the points. It was it for the 1 second. So after the Fourier transform, when we plot the dynamic spectrum and this also, so each of the frequency column, so we take the collections, right? We take 100 samples and then sum them over. So each time point is like we take the average of those 100 time points, or like we can represent it by the end point. Like which one would be better?
It doesn't matter. If you wanted to indicate some time t, then it's best represented by the central time of that window.
Oh, okay. And one minor question, like when I plotted the dynamic spectra for the north antenna and south antenna separately, so the lines which were there, so the contrast was decent enough. But when I plotted AS plus AN, like I added both the voltage and then I plotted the dynamic spectra, so the contrast kind of reduced. Like the lines were not as visible as they were before individually.
The contrast should have actually improved when you added the two, based on how you, even if you added it incoherently, you should get √2 improvement in the contrast. Okay. So please check why your contrast seems to have reduced.
Okay, I'll check that.
What would be expected if you added the voltages themselves or the spectra after taking before modular squaring, then because these signals are expected to be in phase, the instrument was observing them correctly where all the phase compensation was done between the two halves of the array, you would expect twice the signal, and you should get contrast improvement of 2 if you were to add things before modular squaring. And if you added them after modular squaring from the two halves of the antenna, then you will get √2 improvement.
Okay,
I think, can I say something? I think what the problem he's facing, I also faced a similar problem. That's if you do not account for that shift initially, I think it arises because of that.
Which shift?
There's the shift in the mean initially because of the if you do not subtract, because you see that the two voltages, in one case the mean is almost 0, in the other case the mean is not 0.
Yes.
So if you if when we don't correct for that, then I could also see that reduce in the when we
the
added
contrast as seen in the on any scale of representation. Yes, because the scale gets decided by this DC offset.
Yeah.
Right.
Yeah.
And one of them might bring in extra offset when you add it. Yes, that's possible. But I think in terms of the contrast as defined by the random fluctuations to the tallness of the pulse, you will find an improvement. So you can get rid of this DC offset right away in the beginning, and then view after adding or not adding what is the difference you get.
Okay, DC offset would be the mean, right, of the whole sample.
Yeah, there are a few questions again from YouTube. So Sonia Ghosh is asking, why can't we use a lower frequency of observation initially instead of down converting the signal using local oscillator, which was based on the earlier answer from Desh? Is it because of some electronic limitation? She is asking.
Well, I mean, I'll start with the answer. Maybe Desh can add in. But ideally, different frequencies of from a particular source gives us different information. There's no need to choose only the lowest frequencies for whatever reasons. So we might be interested in gigahertz or so on, and that's why we observe in many frequencies. But also there's a problem that the lower frequency you go, it has a lot more ISM effects like dispersion and scattering affects a lot more at lower frequencies. Desh?
Yeah, so, no. So the question, as I understood, was instead of down converting these bands to a lower frequency, why don't we observe at lower frequency?
Yeah, that is the question.
Yeah. So shifting this to a lower frequency within your electronics is not equivalent of observing information at low frequency. Okay. It is not equivalent of making observations of the sources of interest at those frequencies. The information is still relating to the frequencies that were let in by the telescope. Just because we converted that information down to, so it's like, the same person who was on the top floor came down to a lower floor, the person does not change, right?
Yeah, I hope she understands. And the second question is, how does the time resolution related to the dispersion smear?
Yeah, the time resolution you can attain is limited by the level to which you can correct for dispersion effects. It turns out that in principle, you can correct for dispersion effects to a great level, to the extent that completely undoing of the dispersion effects is possible by methods that are like coherent dispersion and so on, which are applied before you take the modulus square of the data. So those are like correcting for the phase changes that have occurred across frequency accurately, and you can get very high time resolution. The time resolution then gets limited by the inverse of the bandwidth. If you're using certain frequency range, spectral range, that, thanks to uncertainty principle, inverse of that limits the instrumental ability to give you finer details in time. The second effect that might stop you from seeing details or getting high time resolution is the scattering that might occur, multipath propagation. Signals come to you directly, but they also sometimes get scattered and take different path before reaching you. So the detour costs extra time for the signal to reach through another path, and you will find that this will smear out the information that was given out at the same time or over a short duration at the location of the source has now traveled differently and arrived at slightly different times to you as an observer, and that has washed out any detail to the extent of to the level of this spread that you have in the arrival times. And that's nicely shown by this tail that you see in the Vela pulsar on the trailing edge, as they say it, where even if there was an impulse given by this pulsar with a very narrow width, you have an inherent smoothing that has occurred because of this profile, which characterizes the response of the medium in between.
Okay, and another question from Sonia, which is related to FFT. So she's asking, how does sampling frequency affect the number of FFT points? Also, how do we choose an optimum value of the number of FFT points, as the frequency resolution has an inverse relation with the time resolution?
Yeah, so the sampling interval is chosen to make sure that you do not lose any information, and we do not waste extra efforts in going for much finer sampling in time than that is needed. So the range of frequencies, namely the bandwidth, dictates how fast we should sample the information, which is simply related to how fast the information might be changing. So we want to catch on all the details, which means we should sample it finer than the rate at which it is changing. And that is leads to this Nyquist criteria, which says that you will, if for a bandwidth B in real sampling, you will need to sample it at intervals of 1 upon twice the bandwidth at least. Okay, if you do not do that, if you do it more coarsely, you might mix the information from one frequency with the other information. So, so that's about the time sampling. Having done that, you now can decide what spectral resolution you want, and based on that, you will be taking the number of time samples associated with the inverse of the spectral resolution you wish to have. It's really your choice. What will be optimum is, of course, where you have fine enough spectral resolution that you can correct for the dispersion effects finely enough, or any detail that you want to see in the spectrum at that fine level. Having decided the spectral resolution, you can compute the inverse of it, divide that by the time interval at which information is available, and that gives you the number of points you should choose for Fourier transforming such a way that you get the level of spectral detail that you desire.
Okay, there's question by Abhishek Jala. Any relation between scattering and dispersion of pulse?
Yes, there is a loose relation between the, there is a causal relation. The same electrons that cause dispersion, if they were uniformly distributed without any irregularities in their densities, then you would have only dispersion and no scattering. The irregularities in the density, that means the density is not constant between you and the source. The electron density is not constant, and it might vary spatially. In space, it might vary sometimes dramatically. You will have these scattering effects taking place. It's like a simple case of a glass slab with a different refractive index, which is at different frequencies. You might get certain dispersion, but if the glass also has roughness inside of the material or even of the surface, you will get scattering. So more the electron density, more the fluctuations in them would be, if the percentage fluctuations are similar. So more dispersion might imply in most cases more scattering. Does it answer the question you had about the relation between scattering and dispersion?
Hope he got it. So yeah, Prakash, you can continue.
Okay. Is
Hello, sir.
go on.
I have a question regarding D-dispersion. When we do
Mhm.
D-dispersion, we'll get the different time ranges for the different frequencies, right? Like
And
you have to
delay
shift.
compensations. Yeah.
Okay, so we have to interest. I mean, what time range we have to choose then for the final dispersion spectrum? I mean, the time range will change. It will reduce probably.
Well, it will become, this rectangle will become a parallelogram, okay, by an amount of the extreme shift, right? There will be two triangles at the edge, which you can neglect.
Okay.
Where you do not have complete data from all the frequencies, right?
Okay, thank you.
Okay. So I would expect for the winter school itself, I think if you can get till this integrated pulse, that would be good, even for the presentations. But you can obviously do much better. You can, instead of these rough DM and period values, you can actually get to more accurate values using your data itself. One of the ways in which we can do that is go by the principle that the effect of an incorrect dispersion measure, which tends to smear the signal in frequency, or a wrong period, which tends to smear the signal in time, is to essentially broaden the pulse. So if you come up with a measure where a narrow pulse gives you a larger value than a smeared out or broader pulse, you can use that metric, go over a matrix of DM and period values, and try to figure out which particular pair of dispersion measure and period gives you the narrowest pulse profile, the final pulse profile that you get after de-dispersion and folding. And that is something that you can do at your own leisure place. One of the measures that can give this, that can give a measure of the narrowness, is to take the sum of the squares of the intensities that you have in this profile. So if you have this profile, it might be better to, subtract, um, do an overall subtraction of a minimum level of intensity that is common to all these DM and period de-dispersion and foldings. And then what you do is you take the square of these individual intensities and add them, and you'll get a single number. Now you can see that any value that is spread over two different bins, when square and added, will give you a smaller number compared to both of those values contributing towards the same bin. So that is essentially the idea of behind this particular metric for determining narrowness. But essentially, you can do that over a matrix of dispersion measure values and period values to get this, get the narrowest profile, and hence correspondingly more accurate DEM and period values for this particular data. Then you can go read up more about this Vela pulsar, try to see what DEM values they have calculated, and then try to see how well they match. So at this point, I'll stop. I'll take a few more questions, maybe, and I think it's almost time to wrap up. The thing with the thing with the worksheets is that I created a short presentation where to summarize the results, but I realized that we are way over time. Um, I mean, I've been getting feedback that you have been working through the worksheets without much problem. What I can do is I'll share the solutions to these worksheets in the same folder where these worksheets were supplied. You can take a look, and we can probably have some after hours session tomorrow or day after if you're interested. I can also start this a separate Slack channel for this if you want to discuss some aspects of it. I'm sure Desh can help out in getting the bigger picture of these things or in some of the details as well. And the rest of it, if you're interested, just email us or let us know, and we can probably discuss this discuss during one of the corridor sessions after the scheduled lectures are over, either tomorrow or day after.